When we think about electricity, we almost always picture power flowing through wires, right? Lighting up our homes, charging our phones, that sort of thing. But what if I told you the real secret of electricity isn't in how it flows, but in what it does when it stands perfectly still? Welcome to this explainer. Today, we're basically going to redefine electricity entirely. We're looking at electricity at rest. It's this invisible force field that lives on the surfaces of literally everything around us. It's kind of like the secret language of matter, and honestly, mastering it completely changes how you see the physical world. Here's a quick roadmap of our journey today. First, electricity at rest. Second, static in daily life. Third, laws of attraction. Fourth, advanced electrostatic principles. And finally, your future in physics.
Okay, let's dive right into section 1, electricity at rest. What exactly is it?
Well, electrostatics is pretty much exactly that. Electric charges just staying put on the surface of an object. To really understand this, we have to zoom way, way in. Everything in our world is made of atoms, right? And these atoms have positive and negative parts that are normally perfectly balanced. But when you rub two objects together, say dragging your shoes on a carpet or rubbing a balloon on your hair, you're actually knocking some of those tiny negative parts, the electrons, off one object and right onto another. That sudden imbalance creates a powerful, invisible force field. It's the exact reason your hair stands straight up, or why that balloon suddenly sticks to the wall. The charges just desperately want to balance out, and they will pull or push on things around them to make that happen. Now that we've got the microscopic mechanics down, let's look at section 2, static in daily life. While we usually think of static as just this annoying winter shock, we've actually harnessed it as a highly controlled, incredibly powerful tool. I mean, look at the sheer variety of applications here. In your office, laser printers use static electricity to precisely attract black toner powder right onto the paper. In car factories, they use electrostatic spraying. They give the paint one charge and the car body the opposite charge, ensuring a perfect, even coat with literally zero waste. Environmental engineers use it in chimney precipitators to pull pollution particles straight out of the smoke before it even hits the sky. At the gas station, grounding wires prevent tiny static sparks from, igniting the fuel. And in hospitals, defibrillators store massive amounts of static energy to release in a controlled burst that can actually restart a human heart. So yeah, static isn't just a shock. It is serious industrial power. Now, what's really interesting about this slide is seeing how perfectly our common daily annoyances map directly to their electrostatic causes. That static cling ruining your freshly folded laundry, that's just your clothes swapping electrons as they tumble around in the dryer. The way kitchen wrap miraculously sticks to a glass bowl, pure electrostatic bonding. When you touch a metal doorknob and get a zap, that's just the extra electrons you picked up from the carpet deciding to jump all at once. Even the dust perfectly caked on a fast-spinning fan blade is pulled out of the air by the static charge the blades build up while spinning. And on a massive scale, lightning is literally just cloud friction discharging a giant spark to the earth. So, we've seen the everyday observations. Let's transition into section 3, laws of attraction, and uncover the hidden mathematical code that dictates all of this. Let's ground the math in something familiar. Picture this classic childhood party trick. You rub two balloons on a wool sweater, and suddenly they repel each other. They push away without ever even touching. Why? Because they've both picked up the exact same negative charge from the wool. And in electrostatics, likes repel. But the real question is, how hard do they push? And that brings us to Coulomb's law, the universal law for charges. The force between two charges is proportional to the product of those charges divided by the square of the distance between them. Now, if this looks a bit like the formula for gravity to you, you have a great eye. It acts very much like gravity, but with one massive difference. At small distances, electrostatic force is unimaginably stronger than gravity. To put that into perspective, just look at this number, 9 billion. In Coulomb's equation, the constant K is approximately 9 times 10 to the 9th power. This incredible magnitude is exactly why a tiny static charge on a plastic comb can easily overpower the gravitational pull of the entire planet Earth just to lift a little piece of paper off your desk. Which leads us perfectly into our next observation. Have you ever noticed your hair standing up as you bring a charged comb close, but before it actually touches your head? Picture this invisible action at a distance for a second. How exactly is the comb reaching out through empty space? Well, it does this through an electric field. An electric field is simply the region around a charged object where another charge experiences a force. It's essentially mapping out the invisible influence of the charge. And understanding the exact math of this field isn't just dry textbook theory. It is absolutely vital for the modern world. It's the exact science engineers use to design the touchscreen on your smartphone, which senses the tiny disruptions your finger's electric field makes when it hovers over the glass. All right, let's step it up and move to Section 4, Advanced Electrostatic Principles. Let's see how this builds into the deeper end of modern physics. Let's talk about electric potential. Think about these two batteries. You know instinctively that a 9-volt battery packs way more of a push than a standard 1.5-volt AA battery, right? In physics, this voltage is electric potential. It's the electrical pressure that drives a charge. It's the fundamental work required to move a charge through a system, and it is the exact pressure that drives everything from the beating of a human heart to the processing power of a supercomputer. Next up is a principle that literally saves lives: electrostatic shielding, or the Faraday cage effect. The rule is simple but brilliant. The electric field inside a hollow conductor is always zero. This is exactly why you're completely safe sitting inside a metal car if it gets struck by lightning. The charge just travels along the outside skin of the metal, leaving the inside perfectly shielded. It's also why the highly sensitive microcomponents inside your cell phone are carefully wrapped in tiny metal shields. It prevents electrical interference from wrecking your device. Now, here's a surprising natural observation that honestly used to confuse me all the time. We've all seen birds sitting happily on high-voltage power lines. Why on earth don't they get completely electrocuted? Well, this brilliantly illustrates our next concept: equipotential surfaces. An equipotential surface is an area where the electrical potential is exactly the same everywhere. Because the bird's 2 feet are on the exact same wire, sitting at the exact same potential, there is absolutely zero difference in electrical pressure between them. And with no difference in pressure, no work is done, and therefore zero current flows through the bird. It's just a perfect balancing act of physics. Here's another really fascinating observation. If you hold a statically charged rod near a thin stream of water from a faucet, the water will literally bend toward the rod. Why? Because water is an electric dipole. This basically means each water molecule has a slightly positive end and a slightly negative end. This dipole nature is actually why water is known as the universal solvent. It's the foundation of all chemistry and all life on Earth, simply because it can electrically pull apart other molecules. Finally, for our advanced principles, we have to look at Gauss's law. This states that the total electric flux through a closed surface is proportional to the net charge enclosed inside it. So think about it. If you're calculating the charge on a massive, complex shape, like an entire city's high-voltage power grid, you obviously can't measure every single inch of wire. Instead, engineers rely on the elegant, complex math of Gauss's law to calculate these massive fields, ensuring the grid functions properly and keeping all of us safe. Which brings us to Section 5, Your Future in Physics. Why does mastering all this theoretical math actually matter for your trajectory? So the crucial point is this: electrostatics is the ultimate gatekeeper for top-tier competitive exams. If you're taking the IIT JEE, NEET, BITSAT, or NEST, electrostatics carries incredibly high weightage. It demands a perfect mastery of vector calculus and 3D visualization. It's the topic that separates the top rankers from the rest of the pack. But way beyond the exams, these concepts are the lifeblood of 21st century innovation. Aerospace scientists use electrostatics to protect satellites from devastating space radiation. Biomedical researchers study it to understand the delicate potential across human cell membranes. And semiconductor engineers, they rely on it to push the absolute limits of computing power. Speaking of computing power, look at this measurement: 2 nanometers. This is the scale of the next generation of microchips. To engineer technology that is this microscopic, you can't just guess. You need absolute fluency in this secret language of surfaces. Understanding how charge behaves at rest is what allows engineers to manipulate materials at the atomic level, driving the entire digital revolution forward. We've covered an immense amount of ground today, right? From the simple friction of a party balloon to the heavy vector calculus of Gauss's law. But before we wrap up, I want to leave you with a real-world engineering puzzle to test your new knowledge. Think about everything we've discussed today. If you were hired to design a perfectly static-free room for an ultra-sensitive computer laboratory, which electrostatic concept would be your most important tool? Think carefully about how you'd control the invisible force field around us. Keep exploring, keep questioning, and I'll catch you in the next explainer.